that a specific consumer will change energy consumption in response to a change in electric price. And that's something, as I said, we took smart meter data and we used some sort of econometric models to basically decipher that particular flexibility of the consumer. And I would like to invite Professor Alan Love to talk about that research with you.
Thanks, Anamika. So let me just start by saying this has been a great project. Anamika and our other colleague in Norway as well, over at Bergland, have been working on this with several students, I guess 3 students now. And so a lot of this work is work of us and others that I just mentioned, including Anamika and also Grishma Mandahar over in our department. So the first thing that we faced when looking at this data was we wanted to look at flexible load, something we could change where people wouldn't take a lot of monetary risk in doing so. And we've seen what happens in some of the programs that have been used in ERCOT. There was a huge expenditure during a freeze that drove market prices really, really high. So one of the things we thought about to minimize risk in this contract design was effectively just changing thermostat settings and getting a payment for doing that. The question is how much. So you give the controller, the power authority, the ability to change the thermostat setting in your house. You get direct response. One of the problems in contract stuff as well with most of the experiments that have been tried is that there's a lapse of continuation, that if you have to have people participating in their houses to change meters, to change thermostat settings, they quit doing it, they tire. So we wanted this thing to be all automated so we wouldn't have that kind of slippage. We wanted to have something that would reduce risk and so on. So that entailed, as Anamika said, looking at things that would give us something about the disaggregation of something that wouldn't affect people so much. And what we looked at were data in Texas, where HVAC use is quite large. In Austin, Texas, the temperatures in the summer frequently go up to 100 and higher, and it happens for months on end. This is some of the information that Anamika put together about HVAC use, and you can see it's a quite large proportion of power use. I'm guessing in Austin, Texas, it's possibly even higher. So the first thing we needed to do this was disaggregation of the data stream, which was an aggregate. So if you look at the older generation of smart meters, which is what we were doing, they don't have the ability to say the HVAC's using this, the refrigerator's using that, the light bulbs are using this. And there's a whole bunch of literature in this area that we discovered. It's called non-intrusive disaggregation. We came up with, I think, a slightly different method. I'm sure what we did new in a number of ways, but we started using hidden state input-output models, which are a form of signal disaggregation. There's a whole lot of specific issues in that estimation, but it falls into a class of things that are certainly machine learning in their nature. But what we liked about this approach is it's more structural. So we could have some notion about what the working elements of it were. From that, we were able to find, in conjunction with this hidden state input-output modeling, and use of something called fast and frugal decision tree analysis, we could tell what the HVAC signal was. And I'll show you some evidence of that here in the next few slides. From that, we estimated willingness to pay. There's a very long literature on willingness to pay estimation. But what you're really dealing with in this area is latent variable models. We don't observe people's direct willingness to pay, but what we do observe are the exogenous factors facing them, including expenditures they're making on energy, and then their energy use. So you can think about the thermostat. If the thermostat's turned to a low household setting, suppose you're in Austin, Texas, and you set the thermostat 68, that HVAC is going to come on all the time. And that's going to give us some notion about your willingness to pay. Well, in contrast, to see the contrast, suppose you're me, and I lived in Texas for 20 years, not in Austin, but over at College Station, which is more humid. And our thermostat would be set at like 82 to save money because I was an assistant professor. So, you know, my my HVAC was going on far less frequently than the person at 68, right? So that's how we can discern willingness to pay, just to kind of give you a snapshot of where that goes. And then Anamika is going to talk about the bilateral contracts. So this hidden state or input-output hidden state model, it actually has an interesting history that has been used in economics for some time. The basic thing that you have are the states that we're interested in are not observed. So I've got this data stream coming in, and I can't see whether the HVAC's in. I want to get the HVAC signal out of all of the mess of things that's happening in that data stream, because all we see is the total energy use on some increment. In our particular data set, we were using 1 minute increment, and we needed effectively test data. So we used data from these Austin houses that are actually wired, so we could tell what was going on in those houses as well. In estimating these hidden state input-output models, we don't need to know that. In order to test how well we're doing, we do need to know that. So you have, in effect, these exogenous factors that are observable. You have unobserved states, and then you have other kinds of covariance that are going into them as well. So in effect, what you can do is set up an EM algorithm, an expectations maximization algorithm, where things happen in kind of 2 steps. And first step, I make a guess about what the states of the world were. And then I use that guess to estimate models of probabilities in the transition matrix and in the state matrix. And then what I do is iterate back and forth until I get convergence. Convergence is guaranteed under fairly broad conditions in this sort of model estimation. And that's what we did. And that literature is pretty established. What's a bit different is that those transition probabilities and the state variable estimates can have these exogenous components flowing into them as data as covariates in the estimation. And so what we wanted to do was look at and see how those covariants were affecting these transition probabilities and knowing what state we were in. The specific algorithms we used, we had to modify things because there's a censoring in the data. There's a whole host of other technical issues about it that are fairly complex. So we wrote our own algorithms to do this, to take into account these other sorts of considerations that were important to get good estimates. But in effect, we used the Baum-Welsh EM algorithm to do the estimation of it. Now, one of the things that Girish mentioned, and it's really important, and to understand the big setting, what we wanted to do in our analysis was look at household by household, not aggregates. So we're doing this exercise for every household. And to do it, we were using our high-performance computer here at WSU. It's called Camiac, where you can effectively put each house on a different node in the core of the CPU and calculate huge, large numbers of these all at once to reduce computational burden. But that was that whole heterogeneity in the consumer household that kind of led to the notion that you can have efficient contracts because you only want to contract with the people that are best to contract with. That has 2 parts. One is their willingness to pay for energies relatively low. So when I pay them not to cool their house, they're willing to do it. And 2, that they use enough energy to make them interesting. And that's going to be effectively what combines what's called an individual rationality constraint, which is I have to want to participate in the program to do it. So this gives you the first sort of look. This is for a house in this Austin data set. And what we have here are the green dots represent states when we're in certain states. And there's states, there's a whole host of issues here, how many states to include in the estimation, because that's exogenous. In our case, we found that using 8 gave us good results. You could estimate, we tried, I think, up to 24 states, which gets computationally huge. And we tried fewer states, but 8 seemed to be a good number. There's probably a paper to be written about that and that choice. We did not write that paper. We just sort of experimented to see what was a good number. The temperature is on the the fine line, if you can see that on the chart. So you can see that some of these states are happening with more frequency when the temperature is high, and what the temperature here was in degrees Fahrenheit, and states are on the left side. Some are happening with higher frequency when the temperatures are low, but there seems to be a relationship between the temperature and the settings. This is taking that same plot and looking at it a much more fine-grained detail. And so what you can start to see here, what we have now is the load, and you can see these spikes happening, and you can see there's some spikes that are higher than others, and you can see some cases where we have very low frequencies of either highs and lows, and some mid peaks. And when you start looking at that, what you can kind of see is the HVAC's coming on, and that's causing a big spike, but that's also happening in conjunction with other appliances. And there's also kind of a time aggregation happening. And the time aggregation is we're looking at 1 minute snippets of time, and there could be partial cycles on an HVAC, for example, in that 1 minute time that's adding to the only a partial effect on the total HVAC load. It turns out most of these HVAC loads are multi-minute durations, so it'd only be kind of on the shoulders of when that HVAC's going on and off that stuff would show up, but it does, and you can see that the algorithms are picking up patterns fairly well. But what we don't know is which one of these states, state 0, 1, 2, 3, 4, 5, 6, 7, is the ones associated with HVAC. We also don't know if there's more than one HVAC state, because it could be that you have HVAC and refrigerator, HVAC and the dryer, HVAC and the hot water heater going on at once. So we don't have all of that sorted out with this sort of input-output hidden state model, but we've got something we can work with. That's what we looked at. So then here's a further fine detail, the disaggregation, kind of explaining what I was talking about, where we're looking at, here's some states where we have these fairly well-defined peaks here, 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 here. These are all going into state 3. You can see from the analysis, there's some up here that are these really high peaks. There's 2 of them going into state 6. This looks like it could be HVAC and something else that's causing that really high peak. The HVAC's obviously kicking in, but there's some base load that's happening, and so on. So what we did was take a look at those HVAC states. And remember, when we did this hidden state input-output model, there's exogenous factors feeding into it. So the exogenous factors we fed into it were of 2 types. One was cooling degrees, because this is summer heat, but the other was time of day. And we know that there's patterns of behavior that are happening with respect to power use. People arrive home at 5 p.m., 5:30. They open the door, cold air runs out, the HVAC goes on. They do some movement in the house, maybe let the dog out. A bunch of stuff happens that starts triggering these responses. So the time of day is sort of measuring not the cooling degrees for us, but it's measuring human behaviors that are in the house that are repeated patterns. So people will tend to do certain things. There's a large discussion about how this looks, but what those regressors were in there, including the data had some complexities where people would go away from work in some of these houses. They would turn their HVAC off on a programmable thermostat, and it came back on at some time before they came home. We can catch those sorts of behaviors as well with our analysis by using multiplicative dummies of these time of day components, so long as they're frequently repeated. So we're trying to capture some of those human behaviors in here as well that are going on. Now, there's a thing I've got circled. This is the lift. And over here on the left, what we did was take the temperature and divide it into 3 ranges. So the low, the temp 1 is like, I can't remember. I think we did 10 degree steps. Do you remember, Anamika? I think that's what we did. So it's like 10 degrees above the cooling degrees. I think cooling degrees are normalized to 67 degrees or 68. And then the first 10 degrees above it would be temp 1. We average those, temp 2, temp 3. Let's see if you can, hope you understand. But from this, it looks like we get the lift. If you go from this is the power use over those rankings in this table, and we go from 16.6 to 21 over those. That gave us a lift of 4.3 I guess those are kilowatt hours, and here's where I'm not an electrical engineer, but it's a lift in volume. Over here, we have a lift of 4, and over here in state 7, we have a lift of 13. Those are obviously those really high peaks that we identified. That gave us the notion about, well, some of the things we want to look at now is we don't know for sure which one of these states is associated with HVAC use. And it looks like there's potentially 3, and the others probably aren't. So we needed a method to allow us to determine which one of these states was actually the HVAC states we were interested in. So we could then use that for our disaggregation and predictions for our willingness to pay and the volumes that we would have in our contracts that we would contract households with. So what we used was something called a fast and frugal decision tree, where we now have, in effect, test data, because we use these houses that were actually wired. And now we really know which times, which data was associated with HVAC on. And so we used that data to go back to the estimates that we were getting with the probabilities of HVAC states being on or off from our hidden state input-output modeling, and found out that a few simple steps we could predict with quite good accuracy which one of these states we were getting out of our hidden state input-output model were actually HVAC states. Okay, so everybody follow what the logic is. I have not seen anybody use this in the literature, and frankly, it was sort of a puzzle when we saw this stuff coming out of this hidden state input-output models. How do you determine what states I'm interested in? And this is what we ended up doing. The benefit of this fast and frugal exercise is it basically looks at decision criteria on your explanatory variables. It's a tree and branch technique, again, a machine learning method. But what it's doing is it's taking all of the different variables that I could cut to find out what state, what leaves I really want at the end. And it assigns to the first step the cut that gives us the highest probability of making the correct statement. And then it takes the variable that gives us the next. And it not only takes that variable and orders them, but it shows you where the cutoff point is for that variable that says you're in or you're out. So in these fast and frugal trees, they're very simple. And that's what we wanted, because we wanted understandable AI. And it gives us the cut point. It says the first thing to look at is cooling degrees. Well, we could see that before from the lift. And it tells you the cutoff point for it. And the cutoff point is, I can't remember, 19.67, that's in the cooling degrees. So that would be in cooling degrees. The next step was afternoon weekday. Well, that's not too surprising. Both of those make a lot of sense. Your air conditioner's on only when you need it with the cooling degrees. And oh, by the way, it's not just that it's the heat of the day, but it's I'm coming home and all these activities are happening. And everybody, you study the stuff more than I do, but there's these typical patterns of having a high peak about 5 to 9 p.m., I think, 7 to 9. And there's one in the morning typically. Depends on where you're at, which one's bigger. We're actually the place where the morning ones are often bigger than the evening ones here in Pullman. But in Texas, that's not the case. Then it shows you how many variables to look at, because each variable either gives me a cutoff, I'm in or I'm out, I'm in or I'm out. So it's just a two decision points for each one. Turned out that this worked really well. So we trained the model using only 10% of the data on the 20 households that we were looking through. That was 334,000 observations, which was just 10% of the data. And the testing was done on the remaining 90%. If you study machine learning, you usually use a much higher proportion of the data than 10%, and then make the projections on out of sample range to see how they worked. Well, it turned out when we did that, we got very, very accurate results with just 10% of the data. Here's the total load. It was 1.77. I was looking at the wrong place on the file. The cooling was 19.7. These give you the cutoff, the weekend. If it's a week, afternoon week, then that true decision gave you the next. This is the accuracy from all of the 20 houses, not just from a single house, using that criteria for these decisions about which states that we estimated, 0 through 7, were HVAC states. we had 92.53% accuracy. And that's not just accuracy from this model, but it's from the combination of looking at the input-output hidden state in conjunction with these cutoff selection points for determining which one of these different states was HVAC. Our precision was 95%, sensitivity was 86%. So our miscalculation our misclassification was relatively low. So that gave us a pretty good feeling that we could take an aggregate data stream and actually split it up and disaggregate into the one thing we're interested in. We're not trying to project how much the refrigerator used. We're not projecting whether you had an electric car you're plugging in. All we were really wanting was that HVAC. So we're going to design contracts around it in order to reduce people's risks and get sort of a direct mechanism for power control. So the next part of what we did, and I put a little detail here, it's because this is more of an economics thing, but back in the 1980s, environmental economists started looking at trying to estimate willingness to pay for things that were kind of unobservable and looking on behaviors. There's a lot of proposals, some dealing with transportation costs. I want to find out what a recreational site's worth. What I can do is go visit that recreational site, maybe put a camera up, look at a bunch of license plates, see how far people travel from where their license was to where the site was, which gave me a notion of their opportunity costs of getting to that site and using it. That's just sort of an idea. I can't directly observe these things. How do I do it? The other ones that came up with were looking at contingent things through surveys. And it said, okay, would you be willing to pay some amount of money to save something environmental? Classic examples, whales flying, how much would you be willing to pay to do it? And the problem that they had with these surveys is if I ask you, how much would you be willing to pay to save the last blue whale? You might say, well, I'd pay $5. It would be worth it. But if I ask you a different question, I get a very different result. And the different question I could ask you is, how much would you be willing to accept company X effectively slaughtering the last whale? And you would say, I don't think I would accept $5. I would accept, I don't know what, but a lot more than $5, right? And so depending on how you frame these questions, you get very, very different answers. Now, we have a pretty neat situation here because we're seeing real actions take place. We're seeing people move their thermostat, so it results in different frequencies of HVAC events. So that gives us a very rich environment to use the techniques from what I just talked about called contingent valuation to do this estimation of willingness to pay. So this slide explains it. In effect, what it amounts to is I calculate the cost of expected cost of a cycle of the HVAC, and that's here in this line, this KT. This is the change in the quantity of power I'm using times the price of the power. That's what pi t is. And then I say, well, if it's 1, if the willingness to pay exceeded the cost, okay, clearly it had to be because I did it. I set my thermostat so that was happening. And it's 0 otherwise. If it's below it, I wasn't willing to do it. So in a way, there's some elements here about what's the duration, what are the thermodynamics of the house, which is also doing it. But if I'm looking at a big data set, that kind of averages out, and what I'm seeing is increased frequency. So while the willingness to pay is not directly observable, as we see up in this line I'm circling here, willingness to pay is equal to some stuff that's a function of cooling degrees, some household factors, and some other things. What I can do is set up a likelihood function where on an on event, I do have the expected cost, and I have these covariates, and I have an off event, and I could set up a likelihood function that will give me an expected value for willingness to pay. So it's a very fast summary of 20 years of economics in this area, but that's effectively what happens. It's not, I want you to understand it's not magic. It's based on observables and then using this notion of having these variables that we don't directly observe. We can make references and inferences about them from revealed preferences of real events and things that are happening. So that's what we did to estimate willingness to pay. I do want to make one further comment here. And I'm sorry, and I'm probably running way out of time. But the comment I want to make is one of the things that's really cool with looking at this disaggregate house by house. There's a whole lot of these studies that are done where, you know, I need to know insulation. I need to know square footage. I need to know the vintage of the house. I need to know what kind of windows were installed. I don't need any of that, because as long as none of that changes in the house, it's all falls out into the constants of these estimators. So by doing this disaggregation, I don't need all this detailed information that, you know, an engineer might use to project the thermodynamic use of power. It all falls out in the constant as long as it doesn't change. That also includes things like, well, education, income, you know, a whole host of how many children we have in the house. So there's a whole host of data that you would maybe think I need, but because we're doing this disaggregation household by household, so long as those covariants don't change, they're all going to fall into the constant term. So that's a huge lift and benefit from doing this huge computational process where I estimate every household's behavior. But by disaggregating them like this, I don't need a whole lot of data. I can simplify my data needs hugely. So there's sort of this computational burden versus information burden that I'm escaping here. So here's the willingness to pay estimates. And what these are projected, these are the loads. This is our estimated willingness to pay. You can see there's changes in it. Here, I'm going to do one on the temperature in just a minute, but you can kind of see a jump. And that's one of these dummy variables on time. When you get home, I'm using a lot of power, and I'm willing to pay more for it then, in effect. And that's what comes out of this analysis. In the middle of the night, when it's cool in Texas, I'm willing to pay less for the energy use. And you know, many people in Austin, Texas will open their windows in the evening too, and just turn the AC off altogether because it cools off quite dramatically in the evening, typically because of low humidity. Anamika lived there, so I haven't, but I think it's better in College Station. This shows you the relationship between willingness to pay and temperature. Clearly, they're highly correlated, but again, you can see this red lift here. This is obviously from a dependent, one of the independent variables, which is a dummy variable. You can see some other shifts like that along the way. But there's clearly a relationship between the willingness to pay for power and how hot it is. If it gets hotter, people are willing to pay more. Over here, we have the projected for this house. These are 20 cents per kilowatt up to 40 cents per kilowatt hour. And I think that the average price down in Texas was something in the 20 kilowatt hour. It's no surprise these are actually higher valuations than the actual market price for this household, at least for some of them. It would show that even if we'd have to pay them a lot to get them to reduce their HVAC usage. That's what happens here, at least during these high temperature events. There's other houses where those willingness to pay are going to be lower than these 0.35 and 0.4s. For this house, they're willing to pay a lot for power. That's what it comes out to be for HVAC use. So there's no, sorry, please let's sort of explain the estimation, how we got willingness to pay and our HVAC states from segregation.
Thank you, Alan. So we are, of course, running out of time. I'm not going to talk of the full presentation. The slides will be available to you, and we have our publications and all documented as well. So you can read and you can reach out to us if you have follow-up question. I'm going to talk about how this willingness to pay translates to the contract design, and very briefly. So what we were able to figure out so far is that given smart meter data, if you can disaggregate how someone is using, how individual household is using their HVAC, we can figure out what their willingness to pay for electricity is during different times of the day, years, different months or different days of the year as well, and also external temperature, how much they are willing to pay for electricity at given time, right? So once you know that, then you can figure out that when it will make sense to contract with them. So for example, if someone is willing to pay 40 cents for on a really hot day in Texas, then if we provide them an incentive of that, if I curtail your HVAC for 15 minutes at 30 cents, they're not going to accept it, right? So that's the basic idea, that you have to provide an incentive more than 40 cents, right? Now you can imagine that, okay, if that's the case, if I know willingness to pay for every house, why don't I just simply pay a different contractual price to everyone and get done with it? Why do we even need a contract design or basically figure out what the actual, how many customers I should contract with, at what price I should contract with, and how often should I execute or enact these contracts? Why do we even I need to figure that out. The reason is that it's a regulated entity that you are working with. You cannot provide a different contract to different person based on individual understanding that you have got from these consumers. So you have to figure out a contract that makes sense for all the consumers that you have out there, right? And when you get to that point, it also makes sense for you to think about that when it makes sense for me to contract with the consumers who can provide a large amount of flexibility because they have bigger HVAC size, but because they have bigger HVAC size, it's possible that they have larger footprint of the house. So in that case, they will also have higher willingness to pay for electricity, and maybe I need to pay them more to get that particular response, right? So it becomes a trade-off whether you want to contract with a large number of small consumers or small number of large consumers. And that's really the problem of contract design. Given a set of consumers you are serving, what contract should you have with them which is most optimal for you, but at the same time your consumers are willing to accept it and actually respond to it when the situation when they're called upon. So that's the entire contract design problem. And really it boils down to an optimization problem where we figure out how to incorporate the objective function of the load serving entity along with the individual rationality and incentive compatibility constraints of the consumer, which is basically coming from the econometric model of this particular consumer. And that's what is explained in these slides. So I'm going to skip through that and not go into formulation. And we had some other things in terms of application as well. But since we have last 4 to 5 minutes remaining, I want to open it up for questions. And I just put this discussion slide in front of you, and you can read through it. And maybe there are some questions we can attend to. Yes, go ahead.
I had a question more so on the economic side that I was curious about, because recently there have been kind of two interesting, I guess you can say case studies for this exact same thing. I forget which state it is, but there was one power company that had smart meters and they were starting to individually control thermostat settings, and then you have Southern California, which is just sort of asking people to opt in. Is there an interest in how willingness to pay changes when it's the individual homeowner saying, okay, I'm going to set it lower to save money, versus they look at their thermostat, oh, the power company raised my temperature?
Yeah, that's a really good question. And that's something that we're hoping to find some industry partners to help us with, because our estimates are obviously based in a different policy regime where these customers are paying fixed price. And so the question is, do these things work in practice once we implement them? I think there may be some emerging data on that from some of the experiments that have done, in particularly California. I don't know what the regulatory agency in California is, but I know they've done some work on it fairly recently. And I honestly haven't seen the results of those because they've been fairly recent studies. But that's something that we would certainly like to do because it is an important question. Building all the stuff, we can use secondary data, we can use your history, but does it actually impact it? Which is, I think, the essence of the question. Yeah. So I think, yeah, good question. The answer is we don't know.
Yep, good.
So the purpose of making the contract design is not for individual customers, but try to get side from the utility perspective. What was the whole idea behind studying the disaggregated customers, like individual customers, rather than studying the aggregate?
Because there is heterogeneity in customers. So if you set up one price, or you just understand the aggregated behavior, then you do not really understand what real response potential is from these particular region. So we are using individual consumer information to design those optimal contract so that we can figure out who is going to respond essentially for this particular incentive price, and whatever we are contracting, is it the most optimal solution from the perspective of energy authority. So it's the heterogeneity of the consumer that you have to capture, and that requires you to model these consumer individually. Besides, you're getting smart meter data at individual household level, so that basically gives you a lot more data to play with, where you can actually figure out at individual level whether it makes sense for us to contract with, let's say, this particular area, this particular region, this particular neighborhood. There are a bunch of those questions that can actually be even aggregated at that particular point to figure out what's going on. So that insight you cannot get if you just work with aggregated data.
Right. And can I just follow up a little bit? So one of the problems with the contract designs we have is an energy programming problem. You guys know energy programming problems are extremely difficult to solve. And we're trying to design this contract with potentially tens of thousands of households or hundreds of thousands of households. So one of the important parts of this paper is the heuristic to solve that problem. But the intuition about this disaggregation is really straightforward, and that if I just order the willingness to pay and look at the volume of power that's used. So some of these houses have huge HVACs on them, some have much smaller ones. I can just order those from smallest to largest, and I can get a cutoff point on that line for the volume I need. And that's effectively how our heuristic works. It's rather than doing that huge energy programming problem, all you have to do is sort them, and those are efficient algorithms that run really fast. So that's kind of another benefit of doing this individual component, and there is indeed a lot of heterogeneity, so we get a cutoff point for that.
Yeah, so for example, let's say the time of use pricing is assigned, right? So time of use pricing is based on the fact that most of the consumers are getting home at this time and they are charging their, let's say electric vehicles at that particular time. The point is that those contracts are more designed from the perspective of energy authority and not necessarily from the perspective of consumer. So that's really where that question arises, that whether consumers are unhappy with it because, you suddenly they're not going to respond to it, first of all, if they really need that energy, because you haven't designed the contract based on how consumer consumes electricity. And even if they respond to, and if you have, let's say, made them contract with you and then you are going to control their resources, then they will be discontented because, of course, you do not know how their energy consumption behavior was. And that was the purpose of this research, that let's actually look the problem from consumers' perspective, figure out individually how they want to consume power based on the data that we have, and let's then design a contract that, based on our econometric understanding of the household model, it makes sense for consumer to accept those contracts and respond to it and not be inconvenienced with it. Now, it's quite possible that our models are not sufficiently capture the consumer behavior, or consumer may change their behavior. So it has to be adaptive in nature as well as to keep on going. But the goal was to really incorporate that consumer behavior using the latent information that we are getting based on their consumption pattern, and design a contract that is more amenable to the particular customer or all the consumers that you're trying to contract with. And the theory that we use is actually coming from economics and with the help of Professor Alan Love. It's principal agent model. So we actually design a principal and a bunch of agent, and the goal is that principal is not only maximizing their own profit or objective, but they're cognizant of the agent's objective and agent's amenability to accepting those contracts. And once you incorporate them and model them properly, you would hope that the contract that you're designing is acceptable to the consumer. It's quite possible that you'll still hear complaint and then you modify your model to include those and incorporate those, because not everything is captured in current behavior, because that's contingent on what external variable you're using to, that's driving that particular behavior. But that's where you iterate and revise it. So that's the summary. Any other questions? Anyone? Yes.
Or that willingness to pay income classes. If you have a very rich posh area, people aren't going to care about that area, then I would always.
So my answer is, I'm sure it is. Probably influenced a lot. We can't tell you that from our model, as I mentioned, because what we're assuming is whatever income was unchanged during the period of our estimation willingness to pay. So all of that information just slips into the constant term, along with insulation of a house and everything else that we're assuming to be fixed. So the remarkable thing is we don't need to know that. It's in the estimation. It's in the estimation because we're assuming it didn't change. If it did change, then our estimates would be biased, and that would be a problem. So kind of making, I wouldn't say a heroic assumption there. I'd say we're making a reasonable assumption that income doesn't change that dramatically. Of course, some households there may be unemployment and other things that happen in each reviews. So is that an important factor? Of course it is. How did we account for it? We accounted for it just like we did insulation and other things that are happening with the HVAC signal that comes out of that in-state whatever. So it's in there, but we can't tell you the dimensionality of it, how important it is. So does that make sense to you? But we could do some studies. It'll be interesting because income distribution and equity issues are a very big deal here.
Like if you do the same study in a different area where obviously the income is changed, but it's averaged over the entire area.
Yeah. Yeah, if we had a rich data set, we could include that as an additional regressor and do some auxiliary regressions where we had cross sections of houses to see that effect. But we're just doing this in a disaggregate house by house basis. So long as income didn't change that year, we couldn't estimate the effect anyway using the technique we're using. So there's pros and cons to get that kind of effect. What we want to do is pool together a lot of houses and then see how that covariant of income or other household characteristics may have changed the power to move. We can't make statements about it with our analysis because of the disaggregation. But the disaggregation gauge has some benefits also. But that's a question we can't answer.
So one way I think about it is that if let's say that there is some consistency in the behavior of what we're looking for. So let's say that there is a household, low income household, there are possibility that the house is not well insulated, right? That's number one. There's a possibility that their thermostat will be running at a higher temperature, right? Compared to the other households which are running at a lower temperature, right? It's also possible that it's frequently turning on and off because the house is less efficient, right? So one way to think about is that since this is a latent information that is already incorporated in how you use your HVAC pattern, the claim we are making is that if we are using the same duration data or same time horizon data for, let's say, one household which is in low income neighborhood and one house which is in high income or posh area, then we might be able to find this differences that for the same external temperature that you are seeing, the willingness to pay for 1 degree heating or 1 degree cooling was different for these two households. So we can make then that interpretation that this household is has low willingness to pay and this high household has low willingness to pay, right?
Yeah.
So then we can basically make some observation after the fact, after you know some of the statistics, let's say about the neighborhood itself, and you can correlate with that data and then say something about it, that this neighborhood has got this kind of, response where you have smaller houses which are less flexible, but they have got low willingness to pay. And then you have larger houses which are a lot more flexible, but high willingness to pay. So that's kind of what we're trying to, if you have really a regional database available for the same time period for multiple houses, you can apply this approach to categorize these houses based on this, and then it can correlate to some other database to figure out whether these kind of correlations exist and how strong they are.
Yeah. No, that's really good. I mean, because so a tool to do that with is clustering analysis.
Yeah.
So you could do that, and in fact, we are doing some of this as well with part of paper we didn't present, where we're looking at how much heterogeneity you need to have robust microgrid markets, and maybe we can talk about that some other time. But yeah, that's a good point.
Yeah, the good thing is that we do have a lot of smart meter data available. So if this tool is something that, let's say, a utility company want to use to figure out how they want to work with their demand side participation program with its consumers to figure out who they want to work with or who they want to contract with, what the contract should look like. The goal, the point is to pool all the information that they have got and start, spitting out these numbers. And that can give them a lot more understanding about the diversity or the heterogeneity of their consumers in that particular neighborhood. Our goal is to now extend this study to incorporate larger data sets. So we did for 20 houses in Pecan Street, which are, one very highly advanced neighborhood in Texas, which has lots of energy efficient devices and building. The goal is now to expand it for more houses, more different communities as well, where we have this kind of clean data available. So that also is coming from Pecan Street. They have got close to 1,000 houses actually in that neighborhood, so we can figure out how these change for different houses. They also have got data in New York area and in California, so we can actually figure out how the regional differences make some differences when we think about the estimation process. So that's where it's going. But as you can imagine, it's a lot of data cleaning and a lot of pre-processing work, and that's a tough thing to do when you are doing trying to figure out some of these hidden factors. All right, any questions online? Okay, so then we'll conclude today's session. Sorry about the technical glitches. Hopefully we'll be in a better shape next week. Bye, everyone. If you haven't signed up, make sure you sign up on the